Hello, everyone, and welcome to the seventh lecture of the information visualization course. Today, we're going to be talking about geospatial and temporal data. So that entails visualizations and techniques for time, also working with geographic information, as well as a bit about working with abstract spatial information. And we're also going to discuss the commonalities between the two. So to give an example of a timeline visualization, we can go back to the roots. We have seen this. This is Napoleon's fateful march to Russia, and as you can see, it's a bit stylized, but it can be viewed as a timeline plot, right? So they have started here, and they have started progressing over time towards Moscow, and then all the way back. So a bit stylized, but there is temporal information encoded already in this work. But to go about this formally, so the basics of visualizing time, we have already been over this. Those are line graphs, right? So we have time on our x-axis. We have the value of our dependent variable, or the variable that the attribute that we want to analyze on the y-axis, and that's the basic time-tested and very well working plot to visualize time. We're going to start there. So here we have an example of an index chart with development of stock prices in time for some technological companies. So there's Tesla, Google, Facebook, Apple, and I'm not sure what F is, but yeah, technological companies. How do we enhance this? It helps very much to add horizontal and or vertical guidelines on hover. So interaction is very important to enhance our basic line graphs, because they can get a bit overwhelming, especially if we're plotting many time series at once. And if you want to go one step beyond, so in addition to showing the vertical and horizontal guidelines, you might want to even reconfigure the visualization completely based on selected point in time. I'm going to leave this as a reference here. So because I mean, clicking away from the presentation didn't work that well for me the last time, but there's this thing called ProtoVis. You can try it out on the link below yourself, and there basically you will see this graph. And when you're hovering over various time points, then basically it will get reconfigured. So the point you're hovering over is going to get reconfigured to a gain loss factor of 0. So you're at the kind of anchor point, and the rest of the plot, like the future, is going to get recalculated based on the development with respect to the point that you have selected. I think it's quite nice. So adding interaction definitely will help you with line graphs. But I mean, obviously, it's not the be all end all saving grace. Otherwise, we could just leave the lecture here and call it a day. So let's delve further. So it's very useful to think about the various aspects of temporal data before we start visualizing, because these aspects are going to drive the way we will visualize things. So there's this article by Enier, I'm not sure if I'm pronouncing it correctly, which gives a nice structural framework for temporal visualizations, and we're going to go over all these aspects and show some visualizations that relate to them. So those aspects are frame of reference. So is our data spatially anchored, or is it abstract? Time primitives. So are we interested in specific points in time or intervals? Arrangement. Do we want to display time in a linear or a cyclic manner? And also the mapping, is it static or dynamic? And there are also other dimensions, such as do we have single or multi-dimensional data, or do we have a 2D or 3D visualization? But we've been over these aspects in previous lectures. So frame of reference. So we can either have spatial data, so we have some developments in time at given points on the map. So that's also one of the reasons why why the geo and temporal data have been bundled together in this lecture. And we also have abstract. So we are interested in developments over time, but we are not plotting them on the map. So an example of so we have examples of two plots. One is a growth ring map, one is the horizon graph. We're going to go over both. So the growth ring map looks like this. Here we see a portion of Switzerland, and here we see some rings, color rings on the map, and we're going to unpack what that means. So the growth ring map shows number of photos taken. So each of those rings is basically the size of the growth ring is the numbers of photos taken. The color hue gives seasonality, and color intensity gains yearly variation. So basically, the color gets more intense as we go over the years. The method overview is that each photo equals 1 pixel, and more at the same location are arranged into a circle. And basically, if you grow the rings, it looks like if you cut a tree, you have the growth rings on a tree. That's basically the logic behind this visualization. And the overlapping growth rings are displaced so that they are not fully covered. Now I realize that I should have probably put this in 2 columns. So I'm going to go back here and kind of reiterate, and I'm going to update the slide so that it's in column. This is a bit confusing. So here we see the ring. So the size of each ring is proportional to the number of photos taken. So let's take this place, for example. So here we see that most of the photos have been taken in winter. So we see the blue color hue here and here. So these could possibly correspond to some mountain valleys or ski resorts even. So we have different hues for different seasons, and we have and as the years progress, we are getting darker in color. And basically, just for the seasons, you just kind of grow the rings apart, basically from concentric from the center. Yeah. So here we see this looks like some winter resorts. This looks like there might be some nice forest with changing trees. So because we see mostly autumn pictures, so you can kind of display seasonality of photos on the map like this with growth ring maps. And they have techniques for overlapping the rings. If you have some popular spots where you would basically not see anything, they do this to combat clutter. There are details about the method in the paper. So if you would be interested in this visualization for instance for your practicals, then refer to the back paper to see how the method is actually done. Yes. Further, we have the horizon graph. So that one nicely shows you the time development for a number of data points up to tens. So how this works is that x-axis is fixed to be time. It's the same across all plots. So this is always time. So here we see it goes from 1976 to 2012, and our plot is unemployment rate and differences to the national average. The y-axis is divided into n parts. So n is the number of shown instances. So here we have the US states. So we have 50 different data points, or time series displayed within one plot. And the mini y-axis of each part plus the same variable. So here we have the unemployment rate. So all of these little sections are mini y-axes that plot the same variable. Color is used here to denote if it's a positive or a negative deviation from the national average. And here note that even though we kind of have spatial information here, right? So US states can be plotted on the map, but here they have decided to focus on the time series development. So this is treated as non-spatial information, and it's just comparison of various states between each other. And basically the fixed x-axis makes comparison very easy. So if you want to see, okay, what happened in 1992, you select your point on the x-axis, and you just draw a perpendicular line, and you can quickly diagnose the data for across all your time series. So the necessary component of this is that you scale the x-axis to be the same, and then basically each of the little y-axes plot the same variable, and they plot it like with the same scale basically. And here we have see an example that we have given in lecture 2. The multi-column arrangement of this doesn't really work that well. So this was in the slide about visual queries that basically to compare finance with government, you kind of have to do this crisscross with your eyes to kind of detect patterns. and it's a bit of a mess, and you have to search. So this is a horizon plot done bad. So you have multi columns, and also colors are overused here. It doesn't seem that they add that much information here. It's just, you know, extra visual clutter for us. So we don't take advantage of the Gestalt law of similarity here. Another visualization that you will have seen that also uses the abstract placement of time series on the canvas is the Gantt chart. That one is very often used for project planning. So here we again have the time axis, and we are plotting intervals of things that need to be done in each plot. We can use colors to categorize perhaps who does what. So here we're booking musicians. So maybe the same person does this and this. So we see that this is some communication. So email bans, review contract negotiation, email blast, radio advertising. So maybe this is marketing people. This is setting up the tickets, and you can kind of see which phases of the project co-occur, and how does the project progress. This is very often used. It's called Gantt chart. And in the original iteration, which dates back to the 19th century, it was pretty much just a bar chart with time, so like displaced bars on the map. And but now we have all these the various dependencies. You can show current status of the project, and there are multiple more encodings that have been used, such as the color coding by worker that is responsible for each of the parts. And further dimension that so we had spatial, and we had sorry, I skipped here. Yes, so we had the spatial arrangement, like spatial versus abstract frame of reference. Now we're going to discuss the time primitives that we are interested in. So we can be interested either in points or instant points in time, or instant primitives rather, or intervals. So I'm going to actually start with the intervals. So we have seen that, for example, on the Gantt chart. So we see kind of like sections of time that need to be reserved for individual parts of the project. So this is clearly a time interval. Now, regarding the points, it's a bit difficult. So don't consider point in this regard as something in the like physics sense. So because like a point in time is infinitely small, right? So here we're talking like a point in time can be a day, you know, or it can be a year. So it's a discrete unit that is taken as a single thing happening in the context of your data. So rather than truly discrete points in the mathematical sense, they are points that are considered discrete, you know. So if you're looking into, let's say we had this plot of Europe, map of Europe with the development of national borders. So there a single point in time was 1 year. So we have plotted the borders for each year. Here, for example, on this plot, which we're going to go through, our basically points are 2 hour sections of the day. But to unpack this plot a bit more in detail. So this type of plot is called a cycle plot, for which we always define what is called a seasonal cycle, and also bins within that cycle. So both have to be some meaningful time units for our purpose. So here in this plot, it's a plot of taxi usage in New York City, the city that never sleeps, lives up to its name. And here we see kind of like a histogram or a bar chart of taxi rides being ordered on average across the entire week, for each basically 2 hour bin within a day. So 12 a.m. to 1 a.m., 2 a.m. to 3 a.m., and so forth and so forth. And they have so this is the average across the week. But but in the bottom part of the chart, we can start seeing some patterns. So here we plot Monday till Sunday. On within each of those bins, we plot Monday to Sunday, and for each corresponding point on the x-axis, we plot the number of rides on average for that particular day. So this is better to see patterns, right? So here, for example, we see 12 a.m. to 1 a.m., which is during the night. So unsurprisingly, and note that the week here starts on Sunday. So this is this is actually Sunday and this is Saturday. So we see that there is a massive increase towards the weekend, and over the week. I mean, Monday, Tuesday is the smallest, and then people start going to the pub more and more towards the end of the week. So that kind of confirms our intuition, right? And we see that during the day hours, the pattern flips. So especially in the kind of rush hours in the morning, in the weekend, people are sleeping. So there are not that many cab rides being ordered on Sunday morning or Saturday morning, but people need to go to work, so the pattern flips. Do we have a question?
Yeah, from Tom. He's asking, this graph seems wrong, right? Shouldn't it be 12 a.m.? Shouldn't it be 12 to 1 a.m. and then 1 to 2 a.m.? Maybe you already said it.
No, I didn't say it. Well spotted. It's I have actually noticed this shortly before lecture, and this seems to be data basically for times that start with this hour, right? So it's basically 12:00 to 1:59 is still called it like 1 a.m. So it's basically the first two digits on your digital clock. It will make sense, right? So I think it's just wrongly presented, but you are absolutely right, because like this we would be missing 1 to 2, 3 to 4, 5 to 6, and so forth. So these are 2-hour bins basically. So we have 12 bins, and each of them is 2 hours of the day. So it's just kind of weirdly labeled. Yeah.
Yeah. Thanks.
Yeah. This is well spotted. Absolutely. It's like that. But anyway, to continue, so the pattern is pattern flips between the weekend and between the working days, especially in the rush hours, which is and around lunch. You see that the pattern is nice, rather even, because people are going to lunch on both weekends and weekdays, right? With a bit of a drop around Monday. Maybe they work harder on Monday in New York. I don't know. So here the cycle is 1 day. So this is the cycle, and the bins are 2 hours 2 hours each. So these are the bins, and this is the cycle. So as we have seen, we plot our temporal data for each bin separately. That's what I just talked about. This is for posterity, for this to be a study material, and the advantage of a cycle plot is that you kind of have to learn to read it a bit. It's not very intuitive at first, but it nicely shows temporal developments that are cleanly separated by bins. And what is a nice part about cycle plot is that if you actually, so here it's kind of made obvious with the averages being actually plotted here explicitly, but even if you don't, then kind of the overall shape of the plot matches the histogram, right? So even if you don't show the top part and you only show the cycle plot, then by the overall shape you can see the development across the bins, which I think is a nice thing. So here we have it explicitly. Sometimes you just see the cycle plot and you infer it from the visualization. Here we have another example where we indeed don't really show where we show the bar chart semi-explicitly with the averages. So this is wildlife strikes on plains in the United States. Our cycle is 1 year, so we're going January through December. Our bins are indeed individual months, and we are plotting, like within each of those bins, we plot the 10-year period from 2000 to 2010. So we see that the worst incidence is July through October, and we see that overall the the number of strikes has increased, especially towards 2010, and there seems to be a consistent drop right after 2000. I don't know, maybe it was maybe it was a bit of a downturn of like, well, fewer planes, maybe after 9/11. I don't know, but we can see the patterns like this as well. So here they have opted for this nice like shaded area version of the plot, which kind of draws attention more towards the overall bar chart, basically, so this makes the bar chart semi explicitly displayed. Yes, and to just go over one more example of the interval. So we have been over Gantt charts. This is kind of a Gantt chart where we have seen for the we have seen this in the intro lecture. It's a classic example of early visualizations from the 1990s, where this was used to plot problematic events or problematic / criminal events in government files. So this again, here you see this is a clear example of interval visualization, that there seem to be color coded intervals mapping various events in this mock person's life. I don't think this is Bart Simpson really. So yet another example of an interval type of time plot in addition to the Gantt chart. The next aspect that we want to discuss is arrangement. So arrangement refers to whether you're displaying the timeline as a line, or if so the linear arrangement, or as a cycle. So you're kind of going over seasons, and you assume that seasons repeat. So the linear arrangement assumes a starting point, and time points are ordered absolutely, so after and before each other. That's the kind of the classic notion of time. And then you have the cyclic, which is excellent for displaying periodic phenomena. So for instance, if you're diagnosing sales, there are strong seasonal patterns in sales data usually. So it's good to make these patterns a bit more obvious. An example of a linear arrangement time plot is the line graph that we have seen before, and many others. Most of them are actually linear. And cyclic is, for example, a spiral plot that we're going to see in a second. So again, linear arrangement examples are very plentiful. Horizon graphs and Gantt charts and LifeLines also all use linear time arrangement. So that's kind of the default. So you usually use the linear, and you go for cyclic if it makes sense for your purpose. So the spiral plot is the motivation is as follows. It's a 20-year-old technique, so it's nothing new. But if you plot strongly seasonal data, so data that repeat in a seasonal periodic pattern, if you show it in a let's say this could have been a line graph, but this seems like a bar chart with many small bars. But here you see that you see multiple peaks, and the seasonality is not that nicely visible. So, but if you arrange it into a spiral correctly, then it will make patterns stand out. So this is probably an incorrect ordering, because here we don't see any seasonality at all. But here, if we order it such that these basically become weekly patterns, then we can see that there are strong weekly patterns in this plot. So what is really important is that we have to arrange the periodic data correctly. So we need to find the correct period if we want to use a spiral plot and convey some kind of message. So spiral plots are usually good if we are trying to convey some kind of message. So to determine the correct patterns, we either have to use analytical methods. So we have to go over the data and find the period somehow, or we can use interaction. So that's another way. So if we do this in the analytics sense, that we are letting the analyst discover their own conclusions, then it's very important to make this spiral plot adjustable and meaningful to the analyst, that they can kind of try to see if configure the patterns themselves, because then if they say, now it clicks nicely, if I set a weekly pattern, then they will come to a hypothesis that, so I see that my data has a strong weekly seasonality, which is very very useful takeaway. So interaction should be probably underlined. So this is important, especially in the analytic context. If we want a more kind of, let's say, one-shot static visualization, then we can do this with analytical methods, because if the patterns are there, then with spiral plot it's very easy to visually verify that they indeed are there. So here it's very very obvious that we have a pattern here. So the spiral works, by the way, I haven't really discussed this. So you start at a certain date here, and you kind of unroll the spiral spiral towards the end date, which is here. And of course, like the more you so as to preserve this being, let's say, a weekly slice, so you need to kind of, so with each successive unroll, you need a bit of a larger space for the same sized data point. Again, details in the paper, but so these are all kind of equivalent points, but they have to grow towards the edges so that they are nicely aligned in a pattern. And this we have seen an example of a spiral before. So this was maybe you remember this plot from when we were discussing the trifecta checkup. This was an example of a V visualization. So visualization that has a very good question. So how does Arctic ice disappear? It has sufficient data, but this is a spiral, but it's not a spiral plot. This is just a line graph that has been arranged in a spiral shape. So we don't see. This doesn't mean that we are starting here at a certain time point and we're kind of unrolling it towards the edges. This is just, this is a distorted.
Hey, 2 more minutes.
Yeah. Okay. So yeah. So this is just an example of a spiral, but not a spiral plot. And unsurprisingly, cycle plots are also using the cyclic time arrangement. So we're not going to explain it again, of course, but this is it's evident that we're using the kind of cyclic notion of time here as well, even though it's encoded differently. So it's directly in the name. I think that we can actually take a break now, and I'm going to see you at 32. All right, so let's continue. Before we start, were there any questions from the previous section?
Actually, yes. Thijs asks, what exactly is the advantage of a cycle point versus a line chart with lines for each day of the week? It seems that would show the same trends, right?
So versus the line, yeah, okay. So yes, but the problem with basically seasonal data, if you plot them in a line graph, is, I'm gonna go back to one of the previous slides, is that it's gonna look like this, right? So you're gonna have all of these various peaks, and sometimes they can be a bit confusing. So I mean, of course, in the sense where you would have like perfectly regular peaks every tick, basically, or every period change, then it would be super easy, of course. But here we, for example, see that this is strongly periodic data. I'm gonna go here so that it's not occluded. But I don't think that this conveys the same message as this one. So here we see the strong seasonality, but here we see a variance in colors here. So sometimes it's stronger, sometimes it's weaker. So it kind of corresponds to this. But I know that you're asking about the cycle plots. I'm gonna get to that in a second. But so from this, it can be obvious to someone that this is seasonal data, but to some it might not be so obvious. So this, if you use the cycle plot, then you're doing pretty much an extra step of as the data scientist, and you're saying, okay, this is strongly seasonal data, and I'm gonna show you the periodicity. So because you kind of nicely decompose it into the relevant bins, into the relevant cycles, so you kind of set the seasonality beforehand, and then you're showing trends within these bins. So that's what's considered as a strength of these visualizations. So yes, it will basically show the same patterns as a line graph, because I mean it's the same data, right? So it's gonna show the same underlying data, but this kind of emphasizes the seasonality and the kind of cyclic nature, if that's a sufficient answer.
Yes, it's clear. Then Liansen asks, what types of visualizations are most suitable used to detect time patterns by means of interaction?
So yeah, so if you want to detect the patterns, so one way to do this is to try and create a spiral plot. And then if you're going to have, let's say, now I'm going to give like a very trivial example, right? So that you're going to have a spiral plot that's going to have some default arrangement, and then you're going to have a slider below that's going to say okay, so periodicity, and you're going to slide it, okay, so what, 1 week or like 8 days, 9 days, and you're going to play with it. So basically the analyst can play with it and see whether it becomes this, whether it aligns into something nice, and if it does, then they will have discovered seasonality. So, but in general, I say that this would be the strongest. So because cycle plots generally require some premeditation, right? So they require that you said this before, and this would be very kind of confusing to do this with a slider. So if you would say, okay, so I can dynamically slide the periods, or sorry, the cycle and the bins. You could do this as well. In principle, I would say that modern visual analytics frameworks should be able to do this, but things reconfigure kind of wildly. So here you're gonna have like this kind of rolling spiral, which would be, I would say, pleasant, and it would be easier for you to maintain state in your mental model between each steps. This could lead to very wild reconfigurations and a bit of chaos. So I would recommend. I mean, I have never done this really. So an honest answer is that I have never done analytics to really unpack time or temporal data in this manner. But I would lean towards a spiral plot rather than a cycle plot, if that's a sufficient answer.
Yes, he says, thanks.
Very good. So, but if you have follow-up questions, concerns, then feel free to keep posting it in this Discord, and we can discuss it further. Of course, no problem with that.
Yeah, Ahmed is asking in slide 29.
Yes.
The graph is made over a year, or on what time interval?
Well, this is the same plot as we have seen before. So this is it's over a day, right? So this entire thing is 1 day. These are the 2-hour bins. So it's separated into 2-hour periods. There's 12 of them, so 12 times 2, and the individual axes is or sub x-axes rather are weeks. So it goes from Sunday to Saturday. It's the American style week. So this is 1 week. This is 1 week. This is 1 week. This is 1 week, and so forth, basically.
Okay.
Okay, so if we're clear on questions for now, then we can proceed. Another aspect that we want to take care of is the mapping. So are we mapping the time series as static data, or are we mapping it dynamically? So static means that we map time to spatial dimensions on the screen, and dynamic means that we use animations and or interaction. So in that sense, like dynamic, so interaction is always added on top. So we're not going to discuss that separately. Much like in the case of what we discussed, the kind of the dynamically unrolling spirals, or that you can dynamically adjust the period with the slider. Another example of a dynamic temporal visualization is the example that we have mentioned many times already during this course, and that's Rosling's population bubble chart, where you kind of play the timeline. It will iterate from 1800 to I think 2000, and each of those steps is going to be a different year. So that's a way to use animations, which we said, okay, that sometimes it's not the best thing to do, but you can use this to kind of animate time. And actually, if you want to use animations, or like animating time is one of the best uses for animation. So because it's kind of natural. So simulating the passage of time with a kind of like video style play button is very natural to the human eye and mind. So this is the dynamic part. That is already examples that we've been over before, but now let's go over the static and an example of a new plot, which is called the trail plot. So the trail plot is that works as follows. So you basically have your XY space is not none of that is time. So you are plotting two variables or attributes that you're interested in. So here we have a plot that on the y-axis plots the inflation rate, and on the x-axis we're plotting the unemployment rate. So for the purpose of this visualization, the authors have chosen this kind of unemployment slash inflation space. And each of the time series is that for each of the time series that you want to plot is basically that you draw a trail or a curve within this XY space over time. So we start at 1969, we go 1970, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80. So we end at 1980. Then is the part which is not considered as interesting by the authors of this particular visualization. So then we kind of continue going with the curve over the years, moving on to 1992. So the economic boom. So there we see that unemployment rate goes down, and inflation goes down as well. And then with the latest recession, we go again to 2007, and we see that we have a massive increase in unemployment, with inflation rate actually going down. Now in 2010, unemployment recovered, and 2013 we are moving back up here. So this is to show that this crisis has been different than the one from 1969 to 1980, where we have had this maybe more expected trend, where inflation rate goes up and so does unemployment. So everything is globally worse, kind of. Here we see that a bit of a different development. So this is an interesting way to plot time as well. It's very important to connect the time points in the temporal order. So you are indeed drawing the curve, as I have demonstrated on the previous slide, with that you're connecting points that are kind of temporally subsequent to each other. And it's also very important that you mark significant time ticks. So here it's years. So we're marking individual years on the trail to make it a bit more readable, a bit more navigable.
Perhaps it's something for the end, but just a quick question for the spiral plot. Why can we just not use a Fourier transform to find high alignment slider points? That way you wouldn't have to slide and search.
Yeah, so absolutely. So note that I have seen that to determine the correct patterns, use analytical methods, which is indeed what you're saying, or interaction, or combine them, or you can do like smooth animation through various parameter settings, so you can kind of animate it. But absolutely, that's a good idea. You can do that. Yeah. All right. So where were we? Yes. So this has been the trail plot. So an example of kind of another example of static display of time on the screen. But again, most of the plots that we have seen so far have been static, which then can be improved, can and should be improved with interaction, such as in the case of even the basic line graph. But this has been a new plot that we haven't discussed before. It is more kind of tailored towards temporal data. Now, regarding the time perspectives, so time can this is kind of an addendum to the arrangement part. So we can have different ways to perceive time, right? So this is not I'm not trying to make this a relativity theory lecture suddenly, but even in analytics, it's sometimes useful to consider them. So ordered is the default, so things happen one after another in a single thread. Then we can have branching time, which means that we have multiple strands of time that is branching out from a certain common point, which we see, for example, here, drawn conceptually. So, and that one is usually used to facilitate description and comparison of alternative scenarios. So maybe different project paths, different cases that could have happened if we have taken a different decision at a certain point, etc. So that's what we use branching time for. And we also have the multiple perspective time, which is not some kind of parallel universe stuff, but rather that you have that you provide a point of view on the passage of time through the lens of various variables or attributes. So you have like multivariate data that develop over time. So you don't have like just one variable over time, but you have multiple variables that develop over time, and you need to kind of compare and contrast those to give you deeper insight into what was happening at a certain time point. An example of branching time from the casual domain, from the XKCD comics. So here we see a nice chart of plots of various movies. And for multiple perspectives, here we see a bit of a this is just an example of a system called Chronominer. You can see it in action by watching the demo if you're interested. And here we have time arranged in a let's say spiral or circle. It's kind of a hybrid visualization. So we have the spiral, but these are actually full subplots, and different colors. Different colors encode different variables, and we can kind of see the passage of time. This is just a screenshot as an example. It's best to see it in the demo, but sometimes you need to plot various variables on top of each other to really glean some complex insight into what was happening at various time periods. So we're not going to unpack this in big detail, but yeah, this is an example of multiple perspective timeline. So when we are analyzing time series data, the key ingredients, well, A is interaction. So it often helps users if you add interaction so that they can highlight the point in time they're interested in, and then the visualization reacts to this. They can select, they can maybe select 2 points and compare them in possibly a subview. So it's very useful to think about that. It's the cornerstone of any analysis and analytics task. But yes, absolutely do use the analysis if needed. Then we have what is called temporal data abstraction, which we're going to go over in a minute. It's way more simpler than it sounds. There we're basically reducing quantitative variables to qualitative. And we're creating what is called manageable chunks out of our data. So here we're going to be kind of analyzing how the reader's mental model usually works to reading time series data, and what needs to be facilitated in a successful temporal visualization. Then we have our favorite technique, which is clustering. We have heard about this a number of times before. So we just group the data and find representatives. And we can do some event detection where we identify the important events in our data. And in addition to this, we do the analysis of data, such as the one recommended by the student with the Fourier transform, basically. So all that we can kind of front load to the pre-processing that we can discover from the data before we start visualizing it, that should absolutely be a part of our temporal visualization if we're able to do so. So the example of the interaction, we have already been over this. So try this demo out where the line graph is going to get recomputed, rearranged, or in proper interaction terms, reconfigured upon your interaction. then when we are talking about the temporal data abstraction, so creating the manageable chunks, so in the kind of in the official kind of Bible of visual analytics, which is the Illuminating the Path book by Thomas and Cook. It's the definition is that you should create that it's to create an abstraction that conveys key ideas while suppressing irrelevant details, which is I think a simple enough thought. Basically, in general, your visualization needs to allow the user to select relevant information, filter out unneeded information, perform some calculations in the head that are necessary to gain insight in that domain. It's good to be able to sort and to cluster. In this regard, the cluster means that the user can do clustering in their head. So it doesn't mean the clustering as a discipline of machine learning, but that you can create meaningful groups in your head. So it's a bit of a terminological overload in this regard. Again, this is the formal definition. So that formally there are 3 abstraction steps. So first, what you do is you're chunking your y-axis pretty much into the so-called state. So you're observing some variable over time, and you identify let's say meaningful value. So this is a high value, this is a medium value, this is a low value, or you have like some intervals that are meaningful within your domain of knowledge, and you're going to be viewing the temporal information that you're going to see later in perspective of this so-called state. And then when we see development over time, so of course we're interested in the gradient. So that's the sign of the derivative in this regard in the event. So is the curve going up or down? So do we see a positive development or do we see a negative development? And we have the rate. So that is basically putting an ordinal value on the gradient. So is this a low, medium, or high, increase or decrease? So as simple as that, basically. So best illustrated on the example. So I have given some formal definition as stated in the literature, but it's really simple. So again, so here we see again our favorite plot. It's I've shown it a couple of times before. So that's again the stocks with the proto is the interaction. So let's say that here we have the y-axis is our gain loss factor. So it could be, for example, meaningful to say, okay, so when I have a gain, those are positive values. So anything above 0 is going to be positive for me. Anything from 0 to, let's say, 50% is, let's say I'm a very forgiving investor, so I'm going to say it's mildly negative. And if it drops below 50% or even it loses all its value, then I'm going to have a strongly negative opinion, and it's like a strongly negative value for me in this regard. Here we see so negative gradient. I can see the curve going down. Positive gradient, I can see the curve going up. Again, in the line plot, this is super trivial, right? So yes, the curve is going down indeed. So why do we need this kind of decomposition? Because in some of the plots it might not be so obvious, right? So if you have a very very tight spiral plot, then maybe it's difficult to see the gradient over time. Or if you have a horizon plot with lots and lots and lots of those values, or those mini time series, maybe the kind of gradient picture is disappearing from it. So this is this is given on an example of a line graph, but you have to make sure that all these key ingredients are going to be there for the user, no matter the visualization you choose. So that's why we are discussing something that sounds super simple at this point, and putting it together like basically the gradient with the rate. So let's say that I'm focusing here on the Amazon stock, and here I see this is a high / strong increase. So the curve goes up, and but I can also see by how much in relative terms. So this given again on a very simple example. So am I able to determine the state? Am I able to determine the gradient? And am I able to determine the rate? Those are kind of 3 checklist attributes for your temporal visualization that should be conveyed when you're visualizing temporal data. Yeah, this is again an example. It's a very classic example. So the colleagues from Vienna have created a system that monitors the breath of newborn infants, and the small icons basically, so just those little rectangles, show important events. So if the doctor is monitoring it's a very simple technique here. So if the doctor is monitoring the babies, he or she can look at the screen and quickly say, oh, I see some icons there, so that warrants further inspection for me. And if it's without icons, then it's not as visually drawing, and possibly everything is or probably everything is in order. So this kind of draws attention where it needs to be drawn in very critical application, basically. So just to give you an example of a real system that really focuses on this. Uh, regarding clustering of time, so again, clustering, so there's not going to be many different algorithms, but from the visualization point of view, it can be a bit tricky because temporal data is a lot of curves, right? So clustering is a method that works for temporal data quite well, and it will identify the most prominent patterns of temporal development among data instances. Yeah, so that's exactly what you would expect it to do, but it will look like this, right? So if you're going to if you go, so this is a graph of total electrical kilowatt consumption somewhere, and here we have this kind of time cube. So here we have days, we have hours, and we have kilowatts is our z-axis. So it's a 3D visualization. We can rotate it here, but you can see that to see patterns here that are beyond trivial. So yes, we can easily see that the consumption overnight is rather minimal and it peaks over the day, but that's hardly surprising. But to really kind of go over this is could be a bit difficult. And I mean, and side note, the chosen color palette is less than ideal. It's rainbow mapped to a continuous variable. So that's a no-no as well. So this is a kind of a bad visualization, right? So how do we view cluster data? So an example of this, so what really works very well is here, if you're looking for daily patterns, for instance, is the so-called calendar view, which is again a classic technique. So here we have a graph of employees over time of the day, and we have various clusters. So one line is one cluster. So this is each line is the cluster representative of typical kind of days. Days across the year, and here we see, so it's a Dutch it's Dutch data, so we can see some familiar days. What is, for example, interesting is that the 5th of December, Sinterklaas, is a cluster of its own. So there is no pattern like on the 5th of December, and it's this one basically. So it's the one second from top. So here we see that people are indeed at work, but they start leaving early. So there are generally, so the orange one is the normal working day cluster. So most of the year except for summer. So we see a lot of people at work. Or the most people at work, and on Sinterklaas we see that there is fewer people in general, and those people that are there tend to leave earlier than on the normal working day. Also, we see that summer is less busy, so we can kind of diagnose the entire year like this, and it makes a lot of sense. So if you actually look at this, it's a very simple visualization, but plotting it here on the calendar with the cluster color memberships highlighted clearly on the calendar, it's surprisingly powerful. So this is something you might want to consider yourself. And lastly, we have talked about event-based visualization in those kind of key ingredients of temporal visualizations. Or this is one of the techniques that if meaningful, it can be very powerful. So again, the temporal data can be a lot of different curves, and sometimes it's difficult to unpack what's happening, or sometimes you will have Okay. Sometimes you will have you will have something happening in the data, but the visualization itself will not show what happened. So sometimes you need to kind of correlate the or to correlate your time series to external events that have happened. So maybe you're detecting events not in the data set proper, but also outside of the data set and placing them in your visualization. So semantic events mean something that has happened. So I don't know, 9/11 or the stock market crash or something along those lines, or 2008 crisis. That's a semantic event. Uh, it has a clear useful meaning to the user. It has a clear start and end in time. So I mean, well, the 2008 crisis is a bit dubious when was the end time, but bear with me. And it's always related to a change of state of a certain set of variables. So something breakthrough happens in your data, and you want to explain it with your visualization. So an example can be like this. So what you do here. So this is a system called LeadLine, where they were computing relationships of people that appear in the news with events that have happened in the news. So here we see that events correlated to Barack Obama were these, and you can kind of view the number of articles that talk about Barack Obama over time and there are events that are marked that drive an increase or decrease in that particular person. And here we have a map where those topics have been discussed over the world. Again, this is an example of a system. The technique here is basically that you take the event and then you plot it on the in your plot superimposed on top of your data, or basically that you can kind of correlate and compare the development of your time series with those semantic events. It really helps explaining. And this is again, this is their model basically, because this is an analytics system. So they have this event identification. They identify entities. So the people / organizations that are being talked about, they kind of put it together. It's called event characterization, and they plot it in the visualization for you to see. Okay, let's take a break now, and we're gonna take care of the questions again at the beginning of the next session in 5 minutes. See you. All right. So, do we have questions from the previous section?
Yes, Ahmed asks, he thinks a triplot is great, but the distance between years are not the same.
Which plot, sorry?
Slide 34.
Slide 34, yes. '34, so that's this one. So we don't.
Okay,
No, the one before. Excuse me.
Okay, here. Oh, trail plot. Right. Yeah. So the distances between the years are not the same. Yes, they are not, because and that's a very good question, and that's exactly why you need to mark the ticks, precisely because the points are not equidistant. Because what you're actually plotting here is that you're plotting the data in this kind of XY space, which is actually inflation rate and unemployment rate. So what can happen is that in 1 year, it can, let's say, I don't know, inflation can grow by 1% and unemployment can stay the same. So you will have a minimal movement, and then in another year you will have I don't know, unemployment rate rising by 7% and inflation by further 7%. So it will go 1 year like this and one year like this, right? And it's completely valid because that is on the underlying data. So these are actually your values for the XY space that you have chosen for your visualization. So indeed, by definition, the plots are not going to be equidistant. So that's why I need the ticks to mark that, okay, this is 71, this is 72, 73. So here what I would expect here is that they have a couple of because the curves are smooth. So I'd expect that they have some kind of curve smoothing technique that they would otherwise look a bit jagged, because you will probably have your recordings for either only the years, or you would have it for number of months. So it would go jagged like that. So they have used this probably some smoothing technique to make it a bit more visually pleasing. But yes, you will not have equidistant points. Absolutely, very good question.
Thanks, he says. And then Liansen asked, how could one detect semantic events in data, possibly AVA system automatically? Are there any techniques for that?
Yeah, so I mean, I'm aware that I am always scratching the surface when it comes to the actual data analysis techniques, right? So this is generally a task for the I'm gonna go to the visualization. Yes. So this is a typical task for information retrieval. So I myself am not an information retrieval specialist, I must admit. There are toolkits for that, I'm sure. But basically what happens is that the task, the information retrieval task, indeed is called topic modeling and event detection. So basically those are all keywords for the information retrieval techniques, right? Because you're gonna have this is articles. So articles are free text. We're gonna talk about text analytics next week on Monday. And again, we're going to be mostly talking about visualization. So I'm not going to be going over the actual kind of AI behind that. But here's, for example, here you have entity extraction, which is part of natural language processing. So if you want a nice toolkit for that, is NLTK. I think it's available for Python for sure. It could be also for many languages. And there you can they have some nice tutorials, and you can also see. I mean, unless you are an information retrieval expert yourself. So I'm not. I don't know what your background is, but. Yeah, so there the entity extraction is basically that you analyze sentences, you remove the so-called stop words, so you and basically the clutter, so the words that don't carry any meaning themselves, and you kind of detect that, okay, the subject of the sentence is Barack Obama, or in this document they're mostly talking about Barack Obama. So that's how you kind of pre-process the data, and then you're employing the visualization technique. So I'm aware that this has been a bit of a broad scope answer. So if you have more kind of follow-up questions, then feel free to ask them, of course. But I mean, yeah, this would be like the general kind of blanket answer to your question.
Okay, thanks. And then Ahmed asks for slide 34. I think Gantt chart is an example. I don't really know.
Mm-hmm.
Yeah, oh, we already were looking at, he already said it, sorry. But then Liansen
This is an example of Gantt chart, right?
Sorry, what like these? No, these are just conceptual depictions, basically, like to just visualize these 3 points. But I would say that branching time is Gantt chart would fall under this
Yes, exactly.
umbrella. Yes.
Okay. Then Liansen asks, what's the link for analytical K?
It's NLTK, so it's Natural Language Toolkit, NLTK. So if you just do these 4 letters and Python, then you should be able to find it. I can get a link for you after the lecture, if you need me to. But it's NLTK, those four letters. Yeah.
All right, thanks.
Yeah. So. Okay, so if there are no further questions, then I can continue. Where were we? Event-based visualization, and here, yes. Okay, this was just pity that I didn't stop on this point before we stopped. The best part about all this I've been talking about is that there's this great resource called the TimeVis browser. So Tominsky and Enyer were doing a big survey of various temporal visualizations in the state of the art, and you can, and at this link you can access all these visualizations. You can filter them by all these concepts that we have learned just now. So for instance, arrangement, linear or cyclic, and you can select your favorite visualizations, use your visualization theory judgment to see which ones work for you, which ones don't, and inspire yourself with in this rather nice gallery. So I recommend visiting this site if you're going to be working with temporal data. The takeaways. So we have seen that temporal data is generally quite prone to clutter, right? So because we have each of the data kind of instances is a single individual time series, which is a curve, not a point, like in the case of normal data. So that will require more space on the screen, and you need to take care of to take into consideration a number of defining characteristics that will drive your visualization, such as frame of reference, time primitives, arrangement mapping, and others, which we have decomposed in the previous part of the lecture. And events and clusters are a basic abstraction mechanism, and you're supposed to let the user analyze meaningful values easily within your plot, whichever you decide. So basically, what is nice, so that's the state, gradient, and rate. So you can as an exercise, if you're interested, this is of course completely optional. You can go select a couple of examples and try to see, okay, can I actually set meaningful intervals for the observed variable? Can I easily see the gradient, and can I see the rate? You know, and that's a useful frame to judge temporal visualizations by. So that will be the temporal data. And now let's go to geodata. So this, why I use this is because even though it's a very early case of visualization in practice, it's a temporal visualization, but it's also a geo-visualization. So this is indeed how it would look on the map if you go from Kovno through Vilna to Moscow. So it's a nice kind of abstract geo-visualization as well. So Charles-Joseph Minard has connected the two topics of this lecture already 150 years ago. So that's why this visualization is the connecting thread of this lecture. And regarding geodata, so geodata comes with a new variable type. So like we had the variables such as ordinal and nominal / categorical and so forth, and we had I don't know, numbers, multivariate. So we have a new variable type here. So we have a geophysical is a variable of its own. It's a tuple which always has to contain both latitude and longitude, and both are needed for valid coordinates. Here we have an example. So this is Amsterdam, right? These two values. The values for latitude and longitude are restricted, -90 to 90 for latitude, -180 to 180 for longitude, and these values are exact, and they are also non-intuitive. So this will pinpoint a fairly particular spot on the map. But if I tell you, hey, let's have a nice weekend at 52.37, 4.89, then you would think me crazy, right? So we need mapping to place names, and place names are categoricals. So for it to actually make any sense for our reader, for our user. And unsurprisingly, a place will comprise a range of coordinates. So this is a coordinate in Amsterdam, but it doesn't mean that Amsterdam equals this exact coordinate, because you should be able to slide on the so it's a range, right? So you can fit Amsterdam in a rectangle or in a 2D shape on the map. So you will have more of these coordinates. In the absolute sense, geophysical data is not really ordinal. So comparing these tuples is not that useful in the kind of less equal or greater operators, because that's only useful if you want to focus on what's more north or south or east or west, which is a very niche thing. We need so for us to be able to do ordinality, or let's say, or some advanced even kind of like ratio style comparisons, we need a reference point or context. So we need distances between the two. So Geophysical data, a new variable. Many of you, of course, already know this, and it needs special considerations. You cannot map it easily directly to other types of data. Before we start drawing things on the map, we have to realize that a map itself is a visualization of the Earth, right? So you know, Earth is a 3D globe. How do we actually project it to 2D, which we then use to project our data on? So note, so this is not a cartography class. We're not going to go over big details, but know that we sort of can project Earth to 2D, but there are always trade-offs. Not all information is preserved, and you need to know what the strengths and weaknesses of our projections are. And this is where dimensionality reduction lessons will apply fully, because we indeed are trying to reduce a 3D object to a 2D object. So we are going to have distortions and so forth. So also what we have discussed in the abstract sense, we are going to see in practice here. So the one that is most widely used, and basically the only one that you kind of need to know for practice is the Mercator projection. That one is used by virtually all online maps, or if you have a GPS in your car, you're going to have a Mercator projection there probably as well. It's a cylindrical projection, so it will map Earth's surface on a cylinder, which is then unrolled. So we see this. This is a picture from Wikipedia. So we can. So mostly it's used in this kind of tangent, not the one kind of slicing the globe, but this one. So you project it on the cylinder, which you then unroll into a map, and you will end up with this classic visualization of the Earth, the classic map of Earth that many of us have hanging on their walls somewhere. What's the advantage of Mercator is that north is always up, south is always down. That's very useful, and east west are always right or left respectively, except when you need to skip the vertical edges. So if you need to go east from here, then you're gonna go here, but you're gonna kind of appear over here. But that's well known, and this is the 180th meridian. So this is a very niche case. On the screen, of course, if you try this on Google Maps, then it will of course preload. So this will be kind of continuously projected next to each other. So you will never reach the edge. So that's a way to do this. And the meridians, so those are the lines with the same longitude are perpendicular to the parallels, which are the lines with the same latitude. So we have this nice kind of 2D grid on top of the Earth. What is really nice about the Mercator projection is that it preserves angles between for example, roads or rivers across the globe. So, and I think that this is probably one of the key reasons why it became a standard for online maps, because and it's related to the problem of Mercator projection, and that is it doesn't preserve areas basically, but we're going to go over that a bit later. So, and consequently, because it preserves angles, it also preserves shapes. Reasonably well, right? So if you go, the closer you go to the equator, the better. There's quite some high distortion towards the poles, because I mean Antarctica doesn't really look like this, at all. So it's the more you're towards the poles, the worse. But in the, let's say, most populated part of the Earth, which is I don't know, the shapes are very reasonably preserved. So that is very useful for navigation, and that's why Mercator has been quite the standard also pre-online times basically. But the problem is that it will distort areas and sometimes greatly. So the closer you are to the poles, the larger the areas appear. And an example that we can give is that Greenland, which is roughly 2 million square kilometers, is the size of Africa. So Greenland and Africa appear roughly the same size, but it's almost 15 times. Africa is almost 15 times larger. So here we have a nice GIF that demonstrates this practice. It animates between the Mercator projection and the true size. If you would kind of apply the equator Mercator projection sequentially across all the latitudes. So here we see that Canada, Russia, Greenland are considerably smaller, and Africa pretty much stays the same. So and Antarctica is probably the most ridiculous example here. So we need to, so yes, Mercator projection that we kind of take for granted is a good one, but it has its own problems, and this is indeed one of the artifacts of dimensionality reduction. Just for you to have a sense to know the different ways to project the Earth, so you can also use the Albers projection, or it can be used. I'm not saying that you should use it, but it's a possibility. That one is a conic projection, so you project Earth on a cone, which has its peak towards the north, and that one is nice that it preserves area sizes. So all across the Earth, you will have the same area, like size in kilometers, in square kilometers, or your other favorite unit, but it will not preserve angles or shapes, which is evident from just looking at the map. So you might think this is completely useless, but it's for example used by the US Geological Survey Bureau. So it has its uses with cartographers, but Mercator is by far the most famous. And now towards geovisualization. So how do we visualize data? So the mother of all geovisualizations is a choropleth. That one is known even without what it does, even without my detailed explanation. So you fill in regions on the map with colors to show a value of a variable across the overall geo area. So here we have an example of population density in Europe. We have already talked about this in the color section of lecture 3. If you're displaying a continuous variable, use one color hue gradient. So don't use a rainbow. Don't map a continuous variable to a rainbow, but rather use a lightness slash luminance based gradient. So here they have done it quite nicely, right? You see that we have this kind of reddish, red orangish shade. We have also talked about the exception that I'm going to reiterate here as well. So if in some cases 2 colors are okay, if there's a clear universally understood value threshold, so if you're doing temperatures, then you can switch from red to blue at 0 degrees Celsius. That makes sense. If your data is categorical, actually, so there's a bit of an exception for an additional exception to the color rule that you're not always using luminance, is that if your data is categorical that you're plotting on the map, you alternate hues so that the plot will not falsely convey ordinality or continuity. So here we have this kind of casual visualization map of a preferred alcoholic drink across countries of Europe. And we see 3 very contrasting colors for the 3 preferred drinks. So categories are best done with separate hues. And again, a tip for software: if you're designing a color map, sorry, the color palette for your choropleths, excuse me, then it's very good to use Color Brewer. It's a free online tool that will allow you to design your palette nice, and it will demonstrate it on the map of the United States as well. So that's a good piece of software that you might want to use also for your practicals. And just a quick side note, it indeed is choropleth, and it's not chloropleth. It's a very common mistake to mispronounce it or write it. And the etymology is that it's from Old Greek, where chora means location and plethos means a great number of plenty. So it literally is plenty of locations basically. So choropleth, not chloropleth. Just to because people tend to make mistakes in this. Extending choropleths to a bit more continuous sense, you can do heat maps on maps. So this is a bit more like a continuous form of the classic discrete choropleth. If you need to show more data than just one kind of color, then you can use what is called a symbol map. These are heavily used in Tableau. And that one is a choropleth plus a very, very simple visualization on top of each region. So that allows investigation of multiple variables in spatial context. Now, it's very key that we are using very, very basic mini visualizations here, because if we recall the laws of pre-attentive display, if all of these is a complex interactive chart, then we are going to be lost in this in a second. So simple glyphs work here. And this is actually an example where pie charts work very well. And I would argue that here it would be maybe even better. Than I haven't seen the alternative of this with bar charts, which where one of the rules that we have learned in lecture 3 is that if you want to draw a pie chart, always ask yourself the question, why not a bar chart here? And the answer for the question, why not a bar chart, because it would be overwhelming here. So here pie charts work actually quite fine. So this is a nice case for them. Of course, we need to be careful about clutter. So it's best to combat it with aggregation on different zoom levels. So when you zoom out, so here we see that this is borderline cluttered on the eastern in the eastern United States. So here we might have opted for that. If you zoom out to this level, then instead of these mini plots, that you would get like a big pie chart here that would show aggregate data for this region, and then when you zoom in, it would split again into the 13 New England states. So aggregation and zooming, so again interaction can help you greatly here. And what I'd like to stress,
like I think 2 more minutes roughly.
Okay,
Maybe.
yeah, perfect. I'm gonna finish this slide, and we're gonna have a break. Yeah. So my last point towards this, the basic kind of visualization, is that please don't overuse maps. So sometimes people are so the fact that you have geophysical data does not mean that it's necessary to use a map visualization or a choropleth. So because you always have to think about whether the geo information is actually relevant to what your visualization tries to convey. So if you, for example, if you will be controlling a brand or a company that sells stuff across the Netherlands, and you're going to be analyzing profits and losses of your stores across the country. So you do know the location of the stores, so you can plot them on the map of the Netherlands. That's fine, but is their geographic location really an explaining factor for their performance? Isn't it like what kind of people you have there, what the campaigns were in that particular region, etc., etc. So there are other explaining factors for your store's performance, probably. I mean, and also the country is geographically pretty homogeneous, right? So yes, there are of course population centers in the Netherlands, but still, like we're not looking at a country that is 6,000 kilometers in let's say width or height. So well, those are bad terms for geographically, but bear with me. So yeah, so don't overuse maps. So if you're analyzing these stores, it's probably not that relevant if the store is in Amsterdam or Hague or The Hague that much. I mean, it's part of the information, because when you encode everything on a choropleth, then the fact that it's on a map becomes the dominant message, basically. So the map is the dominant part of the screen, and people think in geospatial terms immediately. So consider whether you need a map even if you have geodata. So I would like to finish with that point, and I'm going to see you at 36. We're going to see if there were any questions, and we're going to wrap up the lecture. See you. All right, so let's start the final part of the lecture. Are there any questions?
There is a question by Liansen, who asks, how could one best visualize temporal textual data? Some short sentence as an answer. Are there tools available?
Yeah, I mean, it's text analytics design. So basically, you have to design your model, and you have to then visualize it correctly, right? So in the general sense, no, there is not like universal answer to visualize text. You always have to design it yourself to an extent, and we're going to learn that mostly in next week, Monday, I think.
All right, that's all for questions now.
Okay. So yeah, so we have also talked about that we're going to be mentioning the commonalities between the two. So how about spatial temporal visualizations? That you have temporal data that you're trying to visualize on top of your space. So not necessarily textual. So that's all data is basically your time series data in this sense. So the simplest approach is to draw trajectories on a map, right? But that is of course prone to clutter, because each of those data points is a curve, and you're going to fill up the space very easily. So generally, how this is done is that we use the so-called space-time cube, where the xy is the longitude and latitude, and z is the time, basically. So it looks something like this. It's you have your map in the underlying on the camera on the bottom, and then you're plotting the curve over time. So you kind of rise up on the z-axis as we proceed with the time. And much like with 3D scatter plots and 3D visualizations in general, rotation is very key here. So we need to be able to rotate this for maximum performance. This is an example, kind of like an old example, but of still a very nice visual analytics approach, where you do event analysis using spatial temporal cubes. So that's from a system called Oculus from 2004. And regarding the commonalities between time and space from the theoretical perspective, so in both domains there are very strong dependencies between observations. So one point doesn't mean much usually, but it could mean a lot in comparison to other points, right? And what is called the Tobler's first law, I think that comes from cartography, is that everything's related to everything else, but near things are more related than distant things. You know, it's a simple observation, but it works quite nicely. This will allow you to interpolate and extrapolate. It will allow you to integrate information from different sources or of different types, and because you'll be using references to common locations and or timeframes, and so that is actually nicely visible here. So this is a taxi hit and run report, that basically a taxi has run over someone in I don't know what in some city, and I don't know which one this is. And here you can see the common kind of references is that here's something weird has happened. This is the time where the hit and run occurred, and we have like that he has accepted a fare, he parked and refuses a fare. So you can kind of use these events as anchors to kind of guide your analytics. So this is what is meant by integration of information here. And you can do spatial and temporal inference and other stuff, of course. So close and related, right? So if close equals related, then it means that if we take Amsterdam Centraal, the railway station, as a reference point, then point X is going to be more related than the Royal Palace here, right? Well, no, because I mean, if you say that Amsterdam Centraal is close to the Royal Palace, that's a useful piece of information, maybe for tourists. But if you say that Amsterdam Centraal is close to a random point in Het I, which is the body of water next to the station, that doesn't make much sense. So does this actually mean that Tobler's first law doesn't hold? And no, it doesn't, because we need to consider geographic space as heterogeneous. So be careful about that, because relatedness may depend on more factors than just the distance. So it can depend on the distance, but it can depend on the direction that you're taking, for instance, by accessibility via, for example, a means of transport and other stuff. So proximity is therefore a phenomenon dependent. It's going to be reduced to just geographic distance, and it can be defined spatially, but also on other attributes that are ignoring spatial characteristics. So Tobler's first law does hold, but you have to take care of the context as well. And now, if we talk about spatial data in more abstract sense, so if we don't have necessarily geospatial data, we can have geospatial data, but not necessarily geospatial, but also spatial. What is the extent of a single point, right? So what is the neighborhood of a single point? What is the kind of area that is related clearly to a single point and not the others? And if you start thinking about it, then you clearly come to the conclusion that indeed it depends on the other points in the data set. So we have said that spatio-temporal data is highly contextual. So this is one of the places where it shows in full, basically. So the size of the neighborhood or of the domain of a single point is related to how close the other points are. And we actually have a visualization for this. It's called the Voronoi diagram, where you decompose the plane into regions such that for all points in one region, one specific point in your data set is the closest. So this is how you construct it. So regions are intersections of half planes that are leading to convex polygons. So you kind of you partition your space with half planes. And yeah, so here you have so this half plane is the half plane that separates the space pertaining to 1 from the space pertaining to 3. This is the half plane between 2 and 3. So everything here is closer to point 2, everything here is closer to point 3, and so forth. And this is 3 to 4. So everything from here is closer to point 3. Everything here is closer to point 4. And you do this for all combinations of points. And then you slice up your space into convex polygons. So this is a very fundamental data structure for triangulation, for point picking, and showing spheres of influence. For instance, if you want to say, okay, we are urban planners from the city of Amsterdam, and we want to plant new fire hydrants on the map, then you will be doing a Voronoi diagram. So you're gonna see which kind of area is covered by one hydrant, and what is the maximal distance, and so forth. So it's a very useful data structure for this. There are automatic approaches to find your Voronoi diagrams. So you can do this for your data unless it's very high dimensional. It also pays to be aware of the scale, both in the temporal and the spatial domain. This is pretty much just an illustration that fields of domain knowledge can range from nanoseconds to eons and nanometers to light years. So spatio-temporal phenomena, of course, exist and operate on different scales. Probably doesn't surprise us. The correct scale is indicated by the unit scale in which phenomena are measured and aggregated. So, I mean, just read your data, read your context to judge the correct scale. It's, of course, imperative to choose the right scale in order not to miss patterns, because if you have differences in centimeters and you're showing your axes in kilometers, then, of course, the patterns are going to be drowned out by the sheer scale. And the scale should match both the phenomenon and the goal of the analysis. So be aware of that. And more often than not, you will need what is called the multi-scale exploration, which is nothing else than allow your users to reconfigure your their axes, basically. So or to navigate seamlessly to the different parts of the data set. Speaking of smooth navigation, actually in the advanced sense, so not just mere reconfiguration of axes. Suppose that you need to view various zoomed-in locations across a large space. So see that you want to explore the center of New York, and then you want to quickly move to Los Angeles. So how do you do that? So the trivial approach, which is that you're going to be panning zoomed in from New York to LA, is obviously a bad approach, right? Because it will take you a lot of time, and the vast majority of the map sections we'll see won't be relevant at all. So we're going to start at New York, which is relevant, and we're going to slowly move across the United States towards LA. And all we have seen on the way is not relevant for us. It's just distraction, right? So what we can do, we can zoom out, we can pan across the continent and zoom in again. That's better, of course. But how do we actually exactly parameterize this? Or is there a better way to do this so that we're not kind of jumping across the map? So can we do this better? I mean, the answer is yes, we can, and we're gonna go over the overview how we can navigate across the data set in a possibly better way. So this is a nice decomposition. Is like what happens in reality if we're panning and zooming. So the size of the square corresponds to different zoom levels. So this is what actually happens in real life, and this is what we see on the screen, right? So going from this to this. And if we pan and zoom, then and we want to read the word world, then we're not going to read it. We're going to read word, right? So we need to do this smoothly. If we do this with some kind of, let's say, linear transition, or if we do this jumpy, then we might get a wrong message about the data due to the nature of panning and zooming. So, I mean, this paper, which is a reference, it contains a lot of math. So they do it exactly there. But here we're going to see just an overview. So the optimal navigation path should be efficient. So it should go from A to B in as short path as possible. Detours are not appreciated, and it should be smooth. So it should be first and second order continuous. So the reason why they so this means basically that it's going to be smooth transitions between individual steps of the entire animation. So that and this helps you in the analytic sense, because you will not have rapid and abrupt changes to the imagery that you're going to see, and you're going to have better feeling of that you're kind of on top of the data set, right? So if you do these jumpy cuts and pans to different parts of the collection, then it's very confusing. So here, this is so if we do zoom out, pan, and zoom in, then we can do this, but it's not smooth, right? So if we do a better transition model, we may end up with something like this, you know. So here we see that we kind of nicely pan and zoom over the data set, and we kind of see its overall structure quite well. So you can check this out in D3. So there's a way to do this in D3. I have given you a link here directly. So if you have if your visualization is large, you cannot fit it meaningfully on one screen, and you want to navigate across the zoomed out part, and you cannot solve this with aggregation, then smooth navigation is a way to go about this. So for the takeaways of geospatial visualizations, they are of course very closely related to maps, unsurprisingly, and note that maps themselves are visualizations of the Earth. They're not accurate. Scale is very important in the absolute sense to show patterns in the data, and relative is given by the Voronoi diagram. So the scale, so the extent of single point, is that's given by the Voronoi diagram. So how influential individual points are, or like how much space of the map individual points are responsible for. So that's useful for instance for the urban planning. And zooming and navigation, which we kind of take for granted, are also a topic of their own. And smooth and efficient paths result in good user experience. So if you're zooming / panning over a large data set that you cannot fit on one screen, then you need to take care of the zooming and navigation being smooth as well. And the conclusion of the entire lecture. So for the temporal data, judge the defining characteristics carefully that we talked about in the takeaways for the temporal data. We have concluded the geospatial data on the previous slide, and you can combine both by either trajectories on a map or space-time cubes, or sometimes you can use graph-related approaches, which is a segue towards tomorrow, when we're going to be talking about graphs, trees, and networks. So that's it from today's lecture. Do we have any questions?
There are actually no questions currently in the chat.
No questions. Okay, so we can then finish here. Thank you for coming, and I'm going to see you tomorrow. And I'm going to go to Discord, and if you have some questions that came up, I will answer them in text. Thank you for coming.